Okay, welcome back. We're going to do another example of finding the solution to initial value problems using the straight line solution approach, using the eigenvalue and eigenvector approach. Okay, so what we found in a prior work, all right, was that for this system, and it's this linear system of two differential equations and two unknown functions, we found that we had two straight line solutions, and we called them in that video y1 of t, and that came out to be e to the negative 2t times 0, 1, and we had another straight line solution because we had distinct eigenvalues here to this matrix, which was e to the 3t times 5, 1. And that allowed us to build the general solution by taking sums of scalar multiples of these solutions, which we refer to as a linear combination. So that is a general solution to this system. What does that mean? That means if someone gives us an initial value problem to solve, we will be able to find constants k1 and k2 to make, which will satisfy that initial condition. Meaning two things: it satisfies the differential equation, the system of differential equations, and just a quick note, that general solution that we have written down will satisfy the system for any choice of constants k1 and k2. When we're solving the initial value problems, we are enforcing those initial conditions, meaning finding those constants k1 and k2 that will make that particular initial condition valid. So it's a solution to the system always, and then we want to find the specific solution that takes on that particular x and y value at whatever time, in this case t equals 0. Okay, so let's get right after it here. This is going to be similar to what we saw in the prior video. So we're going to use our initial we're going to use our general solution, all right, and we're going to use our initial conditions. Again, I like to put a double-sided equals on here. On one hand, we're given in the problem that the initial condition is 1, 0. On the other hand, we have our general solution to plug in for. When we put t equals 0 in, and that's why in most of the problems in this chapter, the initial t value is 0, because we're going to find exponentials showing up in almost all of our formulas, in almost all of our general solutions. What are we going to get here? We're going to get k1 times e to the 0 power, which is 1, so we won't even write that, times the vector 0, 1, plus k2 times e to the 0, or 3 times 0 power, which is e to the 0, which is 1, so we won't even write that factor of 1 in. Again, we're plugging in t equals 0 to our general solution up above. Okay, now we're going to go through and distribute the constant k1 in and k2 in, and then add those vectors up. So we're going to get a vector equation now, 1, 0 on the left. We're going to have 0 plus 5k2 on the right, and then k1 plus k2 when we add our second components on the right side. And then we just simply set each component equal. The only way that vector equation is true is if each first and second component are equal. So we get this system of two equations and two unknowns. So the system turns into this algebraic system that we have to solve. All right, the first one only has one of the unknowns in it, so we can divide by 5 to find out that k2 is equal 1/5. Plugging that into the second equation, we would get 0 is equal to k1 plus 1/5. Subtracting it over, we get that k2 is negative 1/5. And then we simply just write down our general solution again, substituting, I got a mistake there, that should have been k1 is negative 1/5. All right, and we just simply copy down our general solution, okay, and we're going to substitute in k1 as negative 1/5 and k2 as 1/5. Okay, so we just write that out. So we're going to get y of t will be equal to negative 1/5 times e to the negative 2t times 0, 1, and then k2 was 1/5, positive 1/5 times e to the 3t times 5, 1. Again, we derived that general solution in a prior video, so go back and watch that if you need to. All right, and then we could leave it like that. That's acceptable. All right, on paper, if you want to do something graphically with it, you're going to want to multiply those scalar functions in and then add the results. Multiplying into the first expression, you're going to get 0 in the first component, and then we would get 1/5 times 5 in the second component. I'm just going to do that cancellation and then take it away. 1/5 times 5 will give us 1. All right, so getting rid of that. Now, we were just going to be left with e to the 3t in the first component. That's it. And then we're going to get what in the second component? Negative 1/5 e to the negative 2t plus 1/5 e to the 3t. All right, that's our vector valued function. We'll plot that in Maple later in the video. But as a quick check, what was this supposed to represent? It's a solution to the system that we were given, and moreover, it satisfies the initial condition. If you plug in 0 for t, you're going to get 1 in the first component. You're going to get negative 1/5 plus 1/5, which is going to give us exactly our initial condition, 1, 0. Okay, so there's that one. Enforcing initial conditions is something we're going to be asked to do fairly often, but that's, very important, but not as fundamental as finding the eigenvalues and the corresponding non-zero eigenvectors to then write the general solution down. So this is an important step for sure, but not as crucial. All right, and certainly wholly dependent on us having the correct, a correct general solution out. All right, just a quick reminder before we solve the next problem here, that in that video I have referenced here, I made certain choices to find the non-zero eigenvectors that I came up with. There's not one exact answer for coming up with a general solution. If you wrote down a different eigenvector for each of those corresponding eigenvalues, that's fine. Your general solution will look different. However, when we enforce the initial conditions, we have to come up with the same exact formula in the first component and the second component. It's just that my K1 and K2 would be different than somebody else's. All right, so doing the second part example here, we're supposed to enforce the initial condition that y of 0 is given to be -1, -2. All right, now, again, what we're going to do is just write out the general solution, all right, and then plug in t equals 0 and then set it equal to -1, 2. All right, just as a quick reminder, what's our general solution for this problem? It is K1 times e to the -2t times 0, 1, and then K2 times e to the 3t times the vector 5, 1. Okay, so now plug in 0 to that formula, which is going to again kill off the exponentials, giving us K1 times 0, 1 plus K2. Again, the exponential's gone, times the fixed vector 5, 1. All right, and then we're going to set that equal to -1, -2, that vertical or column vector. Okay, and then we simply multiply out the right-hand side, add up, and then set components equal. So I'm going to skip some of that algebra. The x component on the left is -1. The x component on the right will be 5K2. All right, and then the y component on the left will be -2. The y component on the right will be K1 plus K2. Okay, fine. Now, like the previous example up above, the previous initial condition, we can just divide by 5 to get that K2 is -1/5 in this example. Now we're going to take that and substitute it into the second equation and rewrite that. So we get -2 is going to equal K1, and it'll be -1/5. Okay, now we need to add 1/5 to both sides. Okay, and let's rewrite this as -10/5. Put it as 2/1, multiply top and bottom by 5. Adding those results together, what are we going to get? -9/5 will equal K1. So you might come up with integers, you might come up with fractions when we go through and solve for the constants K1 and K2. All right, now let's write out our solution. Well, then we'll look at the graphs briefly in Maple. So K1's -9/5, and that's going to be times e to the -2t times the vector 0, 1. Okay, plus we came up with, what was it? Should have been plus because K2 was -1/5. All right, so let's get rid of that plus sign and put a minus sign. Oops. So -1/5, and then it'll be e to the 3t times the eigenvector we came up with for the eigenvalue of 3, which was 5, 1. Okay, once again, perfectly okay to leave that like that, or add them together by distributing your scalar expressions into each vector and then adding up. If we do that, the first term from the first vector, the first component for the first vector will be 0. The second one, again, the -1/5 times the 5 will cancel that part out, leaving us with -1. Okay, so get rid of that just to keep it clean. And then what are we going to get? We're going to get e to the 3t power. The second component will be negative 9/5 e to the negative 2 minus 1/5 e to the 3t. Okay, and I'll leave it for you to check that this carries the appropriate initial condition. If we plug in 0, you will get negative 1 in the first component. You'll get negative 9/5 minus 1/5, which will give us, negative 10/5, which of course simplifies down to negative 2. Alright, so we get the correct initial conditions. Alright, so what we did there was we had the general solution from previous work that we built up using the eigenvalue and eigenvector approach. Alright, and then using that general solution we solved 2 initial value problems for that same system. Let's look at what their graphs look like. Let's explore the graphs. Okay, now before we move over to Maple, I'm just going to scroll up a little bit here. We look at our general solution. The first thing that we have here, the first straight line solution, I'm just going to underline here in green, that's what we called y1 before. All right, the other one was e to the 3t times 5/1, that's what we call y sub 2. All right, those were our straight line solutions. If you forget about the k1 and the k2 for temporarily, if you plug in t equals 0 to the first term, you'd get 0, 1. And if you plugged in t equals 0 to the second term, without the k2, you would get 5, 1. So when we go over to plot this in Maple, I've already done that, and I'm going to start out with those straight line solutions. Okay, so here it is. So we've got our system plugged in, and again, in the DE plot syntax here, we have to be with the matrix notation and also the individual component notation. All right, so we had to plug the individual components in as a system, as a list in there, a first and a second equation. All right, and again, we're putting the initial conditions are 0, 1 and 5, 1. And we see we get these 2 straight line solutions. Notice one of them's kind of going out in the first quadrant. The other one's going, the arrows are going inward towards 0 along the y-axis. And we went along the y-axis there because our eigenvector was 0, 1. Okay, 0, 1, which is a vector on the y-axis. Okay, and now I've added in the other 2 solutions, and we can see something a little different is happening. We're going to explore this more in the next section, that we don't have the solutions both approaching the origin here. All right, it's kind of a in-between behavior, and we'll go back to the formula in just a second, but we're not approaching the only equilibrium solution of this system, which is the origin, 0, 0. The only time you approach that as t goes to infinity is if you're along the straight line solution along the y-axis. Otherwise, you're going to tend off towards infinity, tend off away from the origin, further and further away as t increases. Just going back to the formula, why does that happen? Let's look at our last answer here. All right, why does that happen? Well, we've got some exponential growth with the e to the 3t, and we've got some exponential decay. Well, as t goes to infinity, we're going to have exponential increase. All right, the e to the negative 2t term will go to 0. The e to the 3t term will keep growing. All right, that's it for this video.